Oh, this camera's a little off. There we go. This would be a great time to like have the camera shoot right up my nose, but you can't see up my nose because I'm wearing a mask. So, joke's on you. Okay. As I told a class on Wednesday, this is kind of the last big. Hey, Nat.
Thank you.
I'm really sticking with that gun. I'm staying there. But this is kind of the last big huzzah as far as me standing up in this class during this time and just preaching to you about materials and machine design. Okay? If you read through this book, the chapter that shows up after fatigue is chapter 6. Chapter 7 jumps into what is now part 3, design of mechanical elements. Okay. Part 3 of this book, which I believe, I'm not sure there's a part 4. Yeah, no, there is no part 4. Part 3 is, what part 3 does is basically parts 1 and 2 summarize all of the physical principles that guide machine design. Mostly failure, leading to the concept of failure. What part 3 does of our textbook, and what really is scheduled for some of the rest of this class, is how to select and choose components. My goal is that I'm going to be giving you assignments over these, and I'm going to be giving you reading assignments, and I'm going to be giving you lectures online, but I don't really want to be doing a lot of that here in class. This class is intended to be a lot more machine designy, and quite frankly, we haven't really done any design work yet. Does that upset me? Yes, because it's like half of the class name is the word design, but we haven't even designed anything. And if I tell you, if I go back and I give you the first quiz I gave you this semester, which was design a bolt, which, by the way, Scott, to answer your question, I still haven't graded that one. So it's not because you got a 0. Everyone has a 0, and it's because I haven't graded it. Yeah, sorry I didn't respond to you in the email. But if I were to give you that again, it would be a little bit easier because you've done it once. But we still haven't discussed actual design principles. We have talked about failure. Why is failure important in design?
Because you don't want it.
Because you don't want it, or sometimes you do want it, but you want it to be controlled. Okay? Like, say you've got, let's say you've got an element that has a linkage here, and it's being driven forward and backward through a crank motion. Okay? And you specifically design this linkage so that if that linkage is carrying more than 2,000 pounds of force, it just breaks. Okay? You can do something like that. That's effectively what an electrical fuse is. You can do that with a mechanical system. You can ensure that at some critical loading, some component fails. That is perfectly okay. And there are components that are designed to fail. Most of the time they're designed not to fail, as you said. But when it comes to design, failure is a massive criteria. Because as an engineer, most people can do everything else. It's not hard to sit down and be like, well, let's see, I'm designing a hammer. When I design this hammer, I'm going to make sure that it hits nice. I'm going to put a stick and a rock together. hammer. That's not terribly hard. The job of an engineer, determining failure, is a lot of math. This class has been hard because failure is difficult to understand. Okay? But now that you understand the principles of failure, and we're going to talk about fatigue failure today, which is last kind of failure, and now that you understand those principles of failure, now I want to transition into talking about design. Okay? So we'll go through this example today. But we're going to, this class shifts significantly after this point. And this is the reason why I gave you 4 lectures this week, is because I want to be done. I want to move forward. I want to actually get into design work and stop sitting around and doing fun math, trying to figure out stress analysis. So, I'm going to give you an example. The example I'm giving you is basically, let's say you have a stamper machine. Okay? So here you have a stamper machine. And on this stamper machine you have here some kind of a connection to a motor device. And then this stamper bar, which ultimately comes down like this. And as this lifts up, moves around, this bar itself gets in position and causes it to go down. So every time it reaches all the way down, this will stamp and then pull back up, stamp, stamp, stamp. Okay? This is a crank slider 4-bar linkage system. A very simplified version of it. We're going to be talking about crank slider systems next week. A little bit, introduction into it. But what we're going to do is we're going to try to design this linkage here. Okay? And what I'm going to give you for this linkage is the way that it is right now is it looks like this. Okay? It's pretty thick around the 2 connection points. At its cross section here, this is what? 50 millimeters by 50 millimeters square. Okay. What we're going to do is we're going to go ahead and say that because this is a simple linkage with simple connections, simple bolted connections or simple riveted connections, those bolted connections and those riveted connections, you only have 2 of them, which means you know that all of the forces that are exerted between these, it's either going to be tension or compression, because those simple connections cannot exert a moment. And because they can't exert a moment, the force has to lie axially in line with the member. Okay? And this is here, this 50 by 50 cross section represents the thinnest part of this member. So it's the part that we're analyzing critically to see if it fails. Now if you were to do this correctly, you'd plug this into SolidWorks, you'd pull on both ends, see how it works. Awesome. But we're doing it the fast way. If it's faster to do it by hand. You will eventually reach a point in your life where you can do this about 20 minutes by hand. Pretty simply. Gives you a good analysis, makes it easy. Maybe faster than SolidWorks, but this is a great way to check your work. Make sure that SolidWorks is giving you actual, real answers. So what we have going through here is we're going to load this member in compression, really, but it's going to have to accelerate upward and downward. So the force cycle ends up looking, we're going to give it the equation that it is 50,000 newtons plus 150,000 sine omega t newtons. So I guess that's the equation. Okay, and we're estimating that force equation based on what we measured or something. We use a strain gauge, something like that. Okay, so to solve a fatigue problem, it's the same exact steps as a static failure problem, which we did last week, but we have to add in a few things. First of all, we have to determine the effective stresses, and second of all, we have to figure out the endurance limit. Otherwise, it is exactly the same. So, yes, I'm showing you this, and yes, it's at this point, hopefully it starts getting boring. Because if it's boring, it means you understand it. And that's my goal. That's why I'm berating this topic. So, step one, understand geometry. Do we know what geometry we're looking at? Yes. I gave you a cross section. I said it's most likely to fail there because it's thinnest there. Okay, so geometry, check. Step two, understand loading. What is our applied loading here? Do we have an applied loading on the system? Huh? Yes, it's F. Okay, and what is F? Is F axial, shear, bending, or torsion? It's F and it's axial. Do we have any boundary loads? What is a boundary load? Supports, yeah, forces that may be caused by contacting something. It's something where it's touching something else. We don't have, this isn't touching anything else. So we don't have any boundary loads. We only have this applied load and then the load that counteracts it. That's it. Okay, and the only load that we have is axial. So that's nice. We've now listed out what all of our loading conditions are. So step number 3 is come up with the stresses. And here, every one of the loading conditions corresponds to a stress. We're going to take every single loading that occurs and correlate that with a stress that is happening. So, does anybody know the equation for axial stress? Or normal stress? Force over area. Sigma x is equal to fx over ax. It's the actual, it's the simplest stress equation that we have. Okay? And so this is the equation that goes with this loading. Well, that's the only equation we have, because that's the only loading we have. You're not going to have more stresses than you have loads. Asterisk. Because in reality, certain types of loading create different kinds of stresses, but they're so small that we ignore them. So, in any case, this is what we're dealing with. Okay, so now we have our force. We've got our area. We can figure that out. It's 50 by 50 millimeters, which is, what, 1,500 millimeters squared? Yeah! Or something. Okay. Ooh, and I forgot to say, SY is equal to 40 megapascals. If we're going to graph out F with time, okay, we will start at 50,000 newtons. Goes up like this and follows a sinusoid. Okay, what is this maximum loading value?
$200,000.
200,000. What is this minimum loading value? What? Negative 100,000. Okay? So that's good news. What we're going to go ahead and do is we're going to calculate the stresses at the maximum and the minimum conditions. Okay? So, sigma x maximum is equal to 200,000 divided by 200k newtons divided by 50 by 50 is 1500 millimeters squared. So the maximum stress that this encounters is a number. Doing head maths. Okay, so this is equal to 0.1333 kilonewtons per millimeter squared.
Where's the 1500 coming from?
50 by 50 cross section. Big oof. Wow. Did you use a calculator for that?
5 times 5 is 25.
Get out of my class.
That's not.
That is not okay.
That's 50.
Yeah. Come on, man. I wish you could share some of my embarrassment right now. It's Friday. I forgot how to do math. Okay, so as he pointed out correctly, which, by the way, thank you for checking my math. I do appreciate that. This is 0.08 kilonewtons per millimeter squared. Okay, that's not a useful unit. So how do we get to megapascals? Well, a megapascal is a newton per meter squared. So what we have here is if we multiply this by however many millimeters squared or meters squared, which is 1,000 squared. And then, let's see, we gotta divide by 1 kilonewton is equal to 1,000 newtons. So ultimately, we're gonna take this number and multiply it by 1 billion. Okay? And if you do that, you end up getting, all I'm going to do is I'm going to multiply this by 1,000 and then call it megapascals. Otherwise, this is 0.08 gigapascals. That's times a billion. So this is 0.08 gigapascals, which in more reasonable terms is 80 megapascals. Oh, shoot. This SY value is 140, not just 40. Oh, no, it's not. I'm lying to you. Ignore everything I just said about SY. Your material choice is 1020 steel. I'm losing my mind here. My apologies. It's cheap steel. Okay, so that's the maximum stress value. The minimum stress value here, sigma x min, is where we take the minimum loading condition, which is negative 100, and we apply it over the same area. So negative 100 kilonewtons divided by 2,500 millimeters squared. And the answer to that is it ends up being a negative 40 megapascals. You can check my math there, but I mean, it's half the loading, so it's going to be half the stress. So I can do that one in my head, thankfully. Dang it. Because already I'm struggling with multiplying fives. So we've come up with the stresses. Okay, what we're going to go ahead and do is now we take our stresses and we put them in our six axis configuration. Okay. We have a sigma x is it's 80 megapascals max, negative 40 megapascals min, and then every other stress, sigma y equals sigma z equals tau xy equals tau yz equals tau xz equals 0. So we got all our stresses accounted for. Okay? So now we got that. We can plug in this to find our principal stresses. I mean, is this planar loading? Yes. So this is going to be the dumbest calculation we've ever done in this class. Even dumber than that one, and that was pretty dumb. The equation for principal stresses in planar loading are sigma A, sigma B is equal to sigma x plus sigma y divided by 2 plus or minus the square root of sigma x minus sigma y over 2 squared plus tau xy squared. This is 0, this is 0, this is 0. So if you do the math, sigma A is equal to sigma x and sigma B is equal to 0. Ergo, the dumbest equation we've ever used. Thank you, thank you. Actually starting to hurt a little bit now that you do that. So our three principal stresses are going to be sigma x, 0, and 0. Okay, which means our two principal stress states are at max loading, sigma 1 is equal to 80 megapascals, sigma 2 is equal to 0, sigma 3 is equal to 0. At the minimum loading, sigma 1 is equal to 0, sigma 2 is equal to 0, and sigma 3 is equal to negative 40 megapascals. Any questions so far? With the exception of the fact that we had to calculate two different stresses, this process has been identical between static loading and fatigue loading to this point. This is the point where everything changes. Does anybody know what the next step is? It's right before factor of safety. Yeah, it is the endurance limit because we need the endurance limit for the fatigue failure equation. Okay? So, endurance limit. I'm going to go look up in my book and find endurance limit. Okay, I put a couple of questions in your reading assignment about this. But I'm going to ask it to you again. from section 6.7, equation 6.8. S prime E is equal to 0.5 SUT. Well, I gave you the material choice. We're using 1020 steel. We're going to have to go look up what is the, well, first of all, what is SUT? It's the ultimate tensile strength. What does that mean?
The ultimate tensile force that we take before you.
It's the ultimate stress, the ultimate tensile stress that it can handle before it fractures. It is the maximum stress that it can take before fracture, okay? This isn't yield strength. Yield strength is different. To find the ultimate tensile strength, we're going to go back into the back of the book. I believe it's table A20. Yep, going to table A20. And we'll say that this is hot rolled 1020 steel, which means it just comes off the presses looking like that. Cold drawn means that they will, while the steel is cool, they will reshape the steel by running it through rollers or pounding it with presses. We're going to assume that this is just, it's a piece that's cut out of a sheet of metal. Cold drawn steel tends to have higher strength, but also tends to absorb less energy before failure. Cold drawn steel is also a little bit, well, it's harder to do than hot rolled steel. Hot rolled steel is just cheap. Okay, so from table A20, bless you. For hot rolled 1020 steel, which by the way you can find different values for 1020 steel in this book. And the reason for that is just that different people did different tests. That's all it is. So, yeah, actually, it's not for 1020 steel, it's for a different kind of steel, I think. But anyways, it's just different people did different tests. I don't care, as long as you use one, and as long as one of them is right, I don't care which one you use. So this is the tensile strength, SUT, is equal to 380 megapascals. The yield strength, SY, is equal to 210 megapascals. Okay, why doesn't this table give me endurance limit values? Because the endurance limit depends on how many cycles happen. It depends on the material, it depends on the loading conditions. It's not going to be able to tell you that in that table generic for all 1020 steel. It's very dependent on what material you're using. So, yes, you can find tables. If you find a specimen like yours that is loaded to a certain value, you can go up and look the endurance limit, look it up as is tested, and use that straight value. Then you don't need this at all. You just plug in straight value, you're good. Okay? If that's the case, awesome. Move forward, we're done. You can do your own tests to find what the endurance limit is. You can build your own SN curve for your components. And when you do, you find the endurance limit and you're good. No questions. Don't need to do this math. This math exists because we don't have the testing. And all of this math is based on giving us estimates for steel. Okay, and it's giving us estimates for high life cycle for steel. This is after the knee occurs, after you have basically an infinite lifespan for steel. Okay, so that's what this is. What is this factor specifically? What is S prime E? This was one of your reading questions. It's the nominal endurance limit. This is our best estimate that we start with. Okay? The goal is we start with this value and then we modify it based on our loading conditions, based on our material choice, based on everything. So we're going to take, after this, equation 618. This marker's dying. And that is the endurance limit, SE, is equal to Ka, Kb, Kc, Kd, Ke, Kf, S prime E. Okay? Again, this is only true for steels. This is not true for aluminums. Aluminums, you usually have to actually look it up on the table. All right, we have our formulas now. Now we just have to go through and figure out what is Ka, what is Kb, what is Kc. Well, Ka this is the surface factor. It depends on the condition of the surface of the material. The surface of the material is oftentimes will have cracks on it or in it. That's where a lot of disparities come in. So yes, this strongly correlates with the overall endurance limit in fatigue. So Ka equals A SUT-B. We have the value for SUT from table 6.2. This is a hot rolled steel, which means A is equal to 57.7 megapascals and B is equal to negative 0.718. So when we plug this in using an SUT value of 380 megapascals, we get Ka is equal to 0.8108. Yes. So that's our surface factor. Next is our size factor, Kb. If you read through the section on Kb, you'll find that you've got your book open. Look at you being all studious today. You'll find that for axial loading, Kb equals 1. So that's easy. For Kc, Kc is the loading factor. Depending on the modality of loading, that changes Kc. Here, according to equation 626, Kc is equal to 0.85 because we're loading it axially. Next is Kd, the temperature factor. Okay, there's a massive equation that goes along with it. But I'm going to just go look up table 6.4 and say we're operating at around room temperature, which means that our St over Srt value, which is your K factor, is 1. So operating at room temperature, that's 1. Then we go to Ke. Ke is the reliability factor. What reliability do you want for this component? Do you want it to be 50% reliable? And what that means is that if you have fatigue loading near failure limit, then 50% of the components would fail. If you have a reliability of 90%, means 10% of those components being loaded near the endurance limit are going to fail. So do you want 50, 90, 95, 99, 99.9, 99.99, 99.999, or 99.9999? Which one do you want?
Yeah, last one, I think.
Go with, oh, we never want this to fail, ever. We will have, what this means is that you will have 1 in 1 in a million will fail, which I guess is good. Okay, table 6.5 shows you the transformation variable ZA. There's the equation for how to use ZA. And then there is the reliability factor that's calculated straight for you. KE equals 0.620. KF is miscellaneous factors that have to do with corrosion, different kind of surface treatments, and any preloading that may exist in this component or previous damage that may have been incurred. For the sake of this one, we're going to assume it's a brand new component that's just rough steel, and we're going to go ahead and say that's 1. If you don't know what KF is, because it does have some corrosion, you may have to do testing to find it. But if you're going to do testing to find it, you might as well just find the endurance limit. Be done. Okay, so we multiply all of these together. We multiply this by our S prime E value, which is 190. We'll multiply all these together, and we get SE is equal to, I'm doing some math, this is equal to 0.4273 times 190 megapascals, which is equal to 81.19 megapascals. Oof. Question, which is higher, the yield strength or the endurance limit? What? Yield strength, by how much? I'm going to take, Sean, your eyes got really big. I know what that means. By quite a bit. This is substantially smaller than the yield strength. Okay? This is one of the reasons why fatigue is so prevalent in materials and why we have to consider it, is because this kind of loading is much easier to reach than that one over there. Okay, so the next step, now that we've calculated our endurance limit, step number 7, I have run out of board that's visible on camera, which is fun. All right. If any of you come back and watch this lecture later, I apologize for the seasickness. I need to get one of those scrolling cameras. Just move across the room.
Like on the NFL sidelines?
Right, exactly. I wonder if the NFL would loan me one. I also wonder if they let me use their theme song in the middle of class. Like, so this calculation is dun 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 dun. Just to make sure you're awake on the live stream. Okay, so step number 7 is failure theory. Okay, we're going to be using the Soderberg failure theory. I like Soderberg. It tends to be more conservative than the other ones. You can feel free to use another one as long as you can justify it. If you understand what the differences are between them, awesome. They each have their appeal. Each of them is useful in different places. I like Soderberg because it's conservative and it's easy to remember. The Soderberg equation is SE. No. You're reading this in the book, aren't you? It's sigma A over SE plus sigma M over SY is equal to 1 over N. I think. Pretty sure. Yes. Okay, so sigma A, the equation for sigma A is sigma A is equal to sigma maximum minus sigma minimum divided by 2. Sigma A stands for sigma amplitude. It is the amplitude of the variation in stress. Okay? For fully reversed loading, which is, if it was fully reversed, it would be operating around 0, and it would be going between 200,000 and negative 200,000. That's what fully reversed is. For fully reversed loading, our sigma A is 200,000. Okay? And this is where we would just use the equation sigma A over SE, 200,000 loading, 200,000 newtons, and the sigma max value that happens because of that, 80 megapascals over SE 81. But thankfully, that's not the case. Sigma max is equal to 80. Sigma min is equal to negative 40 divided by 2, and we get 60 megapascals. That is the amplitude of the stress change. Okay? Our sigma m value is the median stress value. This is like if you're statically loading it, you're applying this constant loading. This is equal to sigma max plus sigma min divided by 2. Okay, if this was fully reversed loading, going between 200,000 and negative 200,000, then our stresses would go between 80 megapascals and negative 80 megapascals. If that were to happen, what you would end up here is your sigma m value would be 0. It is oscillating about 0. If you plug it into the Soderberg equation, that means this goes away. And the equation I gave you for fully reversed loading, that is the Soderberg equation, just with sigma m equals 0. Okay, so that's why I tried to specify that in that lecture, that it was only for fully reversed loading, because we hadn't gotten into this material yet. Now, sigma max is equal to 80. 80 plus negative 40 divided by 2 is equal to, oh, that's not right, 20 megapascals. So sigma m equals 20 megapascals, sigma a equals 60 megapascals. Now you will notice, because, as Sean's eyes so eloquently stated, I just love how expressive you were right in that moment. SE is so much smaller than SY. Because of that, your sigma m value does not contribute as much to failure as the sigma a value does. The larger the amplitude of your stress change, the more failure you have that occurs. If sigma a is really small, that's good. It means you have a near static loading. Okay? That's always a good thing. The closer you have to static loading conditions, the less likely it's going to be to fail in fatigue. If you're oscillating between 40 and 60 megapascals for your stress, your sigma a is 10 megapascals. So even though, yeah, sigma m is 50 megapascals, you're looking at 50 over SY, 50 over 210, you're still going to have a safety factor somewhere around 4. That's great. So it is your sigma A value that tends to be the most critical, and the reason for that is because your SE value is so much smaller than your SY. Okay? That is the fundamentals of why we're talking about fatigue here. So let's go ahead and do the math. We know our sigma A, we know our sigma M, we know our SE, we know our SY. Let's calculate number 8, which is our factor of safety. So we got 60 megapascals over 81.19 plus 20 megapascals over 210, and that's equal to 1 over n. We do our math here. We get 0.8342 is equal to 1 over n. And so what that means is that n is equal to 1.199. Will this fail? Travis says no. Why do you say no?
Still has that need where the 23% endurance limit, it just stays at that.
It's going to be able, yeah. It's because it is below the SC value, because this is an n value greater than 1, this is going to last forever. And we're predicting this is going to last forever. If you have any variations in the loading, though, if your loading gets any higher than that, you're risking failure. If the loads are any less than that, that's fine. So long as you don't get less than that and happen to go below 100,000 loading in the other direction. That's a different story. Okay? So, now if I were to give you this, if I were to give you this problem backwards and say, you have an n value of 2, design this so that it doesn't fail. And it has to be at 2. 1.199 isn't acceptable. Maybe it's 2 because we're not sure about the loading. Or maybe it's 2 because the loading changes based on environmental conditions. On a hot day, maybe it's higher because the components expand. So let's say this is not acceptable. We have to have a value of 2. What do we do? How do we solve that problem? We give up. We go back and we decide to get a different degree. No, you have 4 variables that you get to play with here. Okay? Does anybody know what those 4 variables are? What?
Can we change that geometry?
Geometry is 1. Oh, I should write over here where you can actually see it, shouldn't I? Yep, you make the part thicker. What other design variables do we have? Yes.
Material.
Material type, yes. And that can be as simple as saying, hey, we're not going to be using hot rolled, we're going to be using cold drawn. Same material type, different treatment. Okay? Different type of the way that it's configured. Okay? That can be all it is. As soon as we do that, this factor of safety would go over 2. Just FYI. Okay? Now, what are the other 2 design variables? What can we change that's going to ultimately change, that's going to ultimately affect the safety factor? I'm just giving you that one. What else can we change? The loading. And I know that seems a little bit weird to say, but when we go to a design problem, you're looking to maximize one of these. Okay? You're looking to see if, for the material you chose, for the safety factor you chose, and the loading condition you chose, is the geometry acceptable. If it's not, you change the geometry. You do it again. Okay? If for the material you chose, and for the loading you chose, and the geometry you chose, maybe you just want to know what the safety factor is. You're analyzing the material as it is. And find your safety factor. Maybe you want a different safety factor, but you're going to reconfigure this because you have to change the loading through that part. You can do that too. To make sure, here's what I have. I need to make sure that I reconfigure the system so I don't overload it. That is another way of designing this. You have these 4 variables, and the way that you change these 4 variables is how you design machines. Okay, that's it for today. This is a lead-in for the lecture I'm going to give you on Monday. I don't want to give you another fatigue analysis design. If you want me to, let me know. I will record another video next week. Okay, I feel like I'm beating this to death at this point.
Feeling pretty stressed out.
That was good. That was good. Feeling very stressed out.